Yes, I'm Edward. I work at Zorp, and we like to say Zorp is the Nock company. So we're in the Urbit ecosystem, but our particular focus is on Nock. And so this is kind of what we think of Nock. Like, you know, in the Urbit ecosystem, we put it on a T-shirt, right? But at Zorp, we'd like to put it in this nice gold frame if we could. So I'm not going to assume any familiarity with Nock, and I'm not going to ask you to memorize this, but I want you to, because the spec was so small in the frame there, I want you to just see it, right? We've got some meta operations here that are just defined in pseudocode. And then these are all of the Nock opcodes. And just very briefly, I want to show you sort of what the correspondence is between these and stuff you might be familiar with, right? So we have an autocons operation. So I can take a pair of Nock what we call formulas. So two Nock, when I say formula, you can think expression. Two Nock formulas, a pair of Nock formulas is a formula that produces a pair of the results. We're working with trees here. So when I say memory read, it's a tree read, not an array index. But we have a index into a tree where you just treat the bits of the index as a path through the binary tree. We can write literals into our programs. We have an operation for constants. We have eval. Think JavaScript or list eval. We can look at a tree and basically say, is this just a leaf of the tree, which is any natural number, or is it a node in the tree? Given a natural number, we can increment it. We can check two trees for equality. We have an if-then-else construct. So here's your conditional, here's your then case, here's your else case. We have linear composition, feed the output. You know, this is dot in Haskell, right? Feed the output of one to the input of the next one. This is, roughly speaking, variable declaration. You flow the input through, but add the, you just make a pair of the output of this one and feed that to this one. This is object-oriented attribute eval. This has a very simple template reduction down to 2. We won't actually talk about it in this talk. And then this is tree editing. So with that same binary bit path, that same index, we can say it's, you could almost say it's a memory write, in that we can have this tree-shaped memory and plug a value, a new tree in at an arbitrary spot in that tree. And then these two are just for hints. We can give hints to whatever our runtime is. These are not allowed to actually change the semantics of the underlying program. And anything else, anything that doesn't match this, we will just crash. OK, so given this nice definition fits our T-shirt, what are we going to try to do today? We're going to try to compile this down to an SSA form program. I have an SSA form LR. You could think of LLVMIR or any crane lift or whatever you wanted to do. OK, but what's hard about this? So why is this an interesting problem in the case of Nock? Well, let's start with this. All of our values are trees. We don't have any. Did you guys see any variable labels in there? Did you guys, right? All of our values are trees. So when you compile C or Haskell or whatever else into SSA form, you, roughly speaking, you generate an SSA value for each variable in your program or for each variable at each mutation site, right? So you have a pretty good idea of where your SSA variables are coming from. So, but in Nock, we just have a tree. So what parts of that tree go in what registers? Oh my goodness, that is going to keep running away from me. Is there a better place for me to stick it? I don't know. So I'll just keep talking while they figure that out. So what we're going to do is we're going to leverage a 1990 technical report by Kent Dybvig when he was at Indiana University called Destination-Driven Code Generation. So when we start walking over this program tree, we're going to feed a goal for our program backwards relative to evaluation order through the program. So we're going to start with the output of the program and make a goal that just says, this is the output of the program. Relatively speaking, you say, this part is in tail position, right? And in general, what we're going to do is we're going to represent our value destinations as a tree whose leaves are SSA values, right? So if you think about a tree of some values, then you think about a probably smaller tree, some of the leaves of this tree are going to correspond maybe to nodes in the other tree, but we're just going to say, okay, this part of the tree goes in this SSA register, and we're just going to feed that backwards. And so this tree that we're feeding backwards as we generate code describes the register placement of an abstract noun, where nouns are values. Nouns are just binary trees with natural number leaves. And this is what that data structure looks like in Hoon. I don't need you to read Hoon. This is a tagged union, right? So we have this case, which is recursive. So you have left side and right side recursive. So this says we're actually going to split up whatever tree comes through here into whatever's described recursively here. We actually have a way to say we don't actually need this part of the tree, right? The computation downstream of this does not depend on this part of the tree at all, so we don't need it. Or we're going to put this part of the tree in the register with this label. So that's fairly straightforward. But that's only half of the equation from destination-driven code generation, because that approach requires both data destination and control flow destination. So our control flow destination is a sum type, once again. And this is where we start with. We're done. We're in tail position, right? So whatever value comes out of the computation with this goal is our result. This computation is being used as the conditional for an if-then-else. So a small weird choice that was made in Nock is to represent true as 0 and false as 1, thus the labels. But if the result of this computation is a 0, you should jump to this label. If it's 1, you should jump to this label. Otherwise, you should crash, is always implied when you're working with Nock. And then the most general case is, here's where to go next. When you're done, here's the label we want to jump to. With your result, we want you to put it in the registers described. If we go back, that's this data structure right here. Okay, so that works pretty well, and I can actually show you some of what that looks like. This is all Hoon, but this is nested pattern matches. Oh, I need to put that up on screen. Okay. Oh, man. Wait, is that readable for everyone, or do you need to go one more zoom level? One more? All right. All right. This, again, I'm not going to ask you to read Hoon. Here's a pattern match, and within this case, the autocons case, this is a nested match on what our goal is, right? So what this is saying is, if we're compiling an autocons, and our goal is we're in tail position, we're done, we want to return this, we're going to generate a new register. We're going to create a new basic block that just has that return instruction from that register. And then we're going to recur without changing what code we're working on and say, please jump to this and put it in this register, right? Because we're actually going to need to make a cons for this. So this is a little bit of avoiding code duplication. So if we go down here and look at this says, if you try to return a pair when you're expected to return a conditional, we know that you're going to crash. So this just generates crash code. You tried to use a pair as the result of a conditional, you can't do that. So here, we're going to look at the need that came in. So if we came from the done case, it's a single register, but in general, it could be an arbitrary tree. And we're going to get back two needs. We're going to get back where do we need to put the result of our left side computation and our right side computation. And this will actually generate code if the need was just to return the whole thing into one register. That will generate the cons operation. Otherwise, it won't generate a cons operation. And so then we'll generate the sub-expression on the right side and the left side, feeding those needs in and sequencing the labels. And down here at the bottom, whenever we're done generating an expression, we return in this form the label for the computation we just generated and how it expects its input, right? So in the autocons case, it's, well, the two sides of the autocons read out of the same the same side. So we're actually going to ask it to please do whatever copy moves are necessary. We can go eliminate moves later. It's fine. But we're in SSA form. For now, we're just going to generate moves, and we'll remove them later. To say, make sure this input is available the way both of them want it. We're not going to go through all of these, but another interesting one to look at is the memory read case. So when you're interpreting Nock in the current runtime, which is called var in the bytecode interpreter, if you do as many people have done and just write a simple, trivial, recursive Nock interpreter, very easy to do, it'll take you an hour or so. When you do opcode 0, which remembers that tree read, you will have your tree fully reified, fully represented in memory, and you will look at that bit stream that's written in the program, and you'll walk down the tree. And taking apart your con cells as you go and pointer chasing. But instead, come on. Where's my actual? Okay, here we go. So this is a fairly recursive function, but the gist of it is, at compile time, we're going to take apart that bit stream, and we're going to build that tree that describes where we want our input to come from the tree that said what we needed. So we were given a tree at the 0 opcode that said where its results need to go in registers. We're going to build a tree path down to that tree, so that tree is now a subtree of what we say we need from our subject, and that's it. In general, we're not emitting any code to do that. All we're doing is changing the description. Where out of our input do we expect our output from? So 0 doesn't do any tree consing, deconsing. It doesn't do any pointer chasing. All it does now is just change how you describe what you expect from your input so that it comes out of your output, so that what you expect of your output is already in the right register when you get there, right? And then for other operations, so where do we actually generate an SSA register in general? We generate it where we actually use a value. So like for Nock 3, we're actually going to inspect the result value and say, is it an atom, which is to say a leaf, or is it a cell, which is to say a node in the tree, right? So we'll generate a register and pack it up as a need for the subformula. All right. So we'll back up here and revisit a small problem and hope Aaron doesn't start jumping up and down and shouting at me. Which is to say, did we notice that there's only actually one operation on atoms, on these natural numbers, which is increment? So what do we do if we want to decrement an atom? This is a general purpose IR. What do we do? Well, the way it's written in Nock, and this is in the standard library for Urbit, you put a counter into your subject. That's the Nock 8. You start it at 0. And then you have a recursive function that increments the counter until it looks and says, OK, would the next increment be equal to my input? If so, I'll return the value that I have now. Oh, this is linear, not in the size of the input. This is linear in the number that you input, which means it's exponential in the size of the input, right? OK, so what does add look like? Well, we're going to take that exponential operation and do it an exponential number of times, counting one side down and the other side up until the side that we're counting down is 0. OK, so now we're like doubly exponential. And then multiply is this pattern again, right? So now for multiply, we're triply exponential. So that means if we, without some solution to this, if we try to write practical computations in Nock, we'll start looking at this, and we'll wait a while, and eventually we'll see this, and we still won't be done. Oh, no. OK, so this was foreseen as part of the original Nock design, it turns out. And the solution is something that we call Chez, which is to say we're going to match the formula, the operation we're doing, and a template on our input. And when it matched, in the interpreter, we're going to run equivalent but highly optimized code in the runtime. So for example, you could say, well, instead of naively running this Nock for addition, we can verify that that's actually equivalent to just what GMP does for addition on natural numbers, right? Okay, so our interpreter will say, okay, this is the formula for add. Let's just use GMP and make the result instead. Okay, that works. But did you notice I said that we'll match the subject and formula template? When do we have to do that? At every eval site. Which means every time we do Nock 2, which is eval, or Nock 9, which is just fancy Nock 2, we have to look at the formula, look at the input, see if it matches some set of template candidates. And so if you look at the most optimized current implementation of Nock, which again is var, and you run a tracing profiler on it, just for like sequential calls, you see this stair step, right? Where the horizontal parts of the stair step are the time it takes to do this, right? This actually, seeing that trace and jumping up and down and screaming was what got me started on this project 2 years ago. Okay, so we're going to change our goal slightly to account for this and say we're going to compile Nock to an SSA form IR with direct calls, meaning that we know what our call targets are at compile time. Otherwise, it's hopeless. We can't solve that problem. So what's hard about this? Oh dear, my slide animation got messed up. Nock doesn't have procedure calls. We don't have variable labels. We don't even have like procedure labels or any way to say statically what code we're going to run at a call site. It's like I said, I walked through, I said, here's eval, here's fancy eval. There's no call instruction in here anywhere, right? So again, 2 is analogous to eval in JavaScript or Lisp. So, and it's slightly worse, this input, which we call our subject, it's both the data that we're going to compute on, and it's all of our library code. So all the other Nock procedures that we might want to invoke are in there. So how do we separate out, this is code that we need to know as part of our input in order to have static calls, from data, which we don't want to depend on when we're compiling, right? Because we like to compile it for more than one input. Okay, so we're going to do a program analysis on Nock where we're going to attempt to minimize our assumptions about the subject while we maximize what conclusions we can draw. And the assumptions are just what is actually in our subject, right? So we have this tree, what parts of the tree are what? And the conclusions are just what are our call targets? What Nock program are we actually going to evaluate at each call site? So we'll have some more data structures. The first one is just a binary tree that just has bits at the cape. So in this case, again, we're going to go with the Nock convention. 0 means yes, there's something here. 1 means no, there's not. And pair is composing this into a tree. So by itself, this answers the question, what part of this noun at this point of the analysis do we need? But we can also pair it with a noun. And then that answers the question, what part of this noun do we know at this point in the analysis? So if we tab back over here. These are those data types. So this means this is either an atom or a cell. In the atom case, it's a bit. And in the cell case, the 2 sides of the cell are recursively this thing, right? So this is just your tree of bits. And then, again, this is literally just pair that with some, so the asterisk here is just the Hoon type for an arbitrary noun, right? So these are the data types that we're going to be pushing through Nock as we do this analysis. So we'll start with this maximizing conclusions step. This is the easier part to think about. We're just going to run Nock, but instead of feeding nouns through it, we're going to feed these noun templates through it. And then when we get to a Nock 2, we're going to look at the value that flowed to our eval site and say, do we know the whole formula? And if so, now we have discovered a direct call site. Simple and easy enough. And module having to check for recursion because we would like our analysis to terminate, we'll just go ahead and recursively evaluate that. So the analysis looks like just a regular tree walking interpreter for Nock. So this is, again, eval. In Nock 2, this is the formula that you're going to run, or how you compute the formula that you're going to run. So if we know the result of this from our analysis, then we can have a direct call. There's a side case where you actually need to intersect this knowledge if you're going through a conditional. If you have your then branch and your else branch, it's fairly straightforward to define what's the intersection of these two things, which is to say, everywhere where I know the same part of the tree from both sides, and they actually agree on the value, right? In any other case, you don't know it, right? And the other thing we're going to do is we're going to, even if we could know what comes out of these, what I would call the real computation parts, we're going to forget it. Because we're doing analysis. We're not actually trying to run the program. So we're going to forget what comes out of Nock 3. We're not going to try to decide statically which branch of the conditional we take. We're going to forget what comes out of Nock 4. Again, because even if we were catching recursion, we would still evaluate add by spinning through it otherwise. And we're going to forget what comes out of Nock 5 for the same reason. All the other Nock operations are either control flow, like eval, or data flow, compose these things in this way. So we're going to actually analyze those, but for the actual do real work operations, we're just going to forget what comes out of them. Okay, so that's great, and it turns out this works very well, right up until you do something like build a loop that accumulates a list. And then your analysis will discover that your subject has changed as regards to the cons tree that it knows, and you'll go into an input loop. So you actually need to only, this is where this originated, you only want to depend for your recursion checking on the parts of the subject that you actually know that you need. And this is the part, how do you track that is the part that is taken by far the longest. Most recently before this, it was an actual literal data flow graph encoding, which was horrifically slow, right? But it turns out all you need to do is track the provenance of these conclusions that you're drawing. And by the provenance, I mean, if we're labeling all our call sites so that we can decorate them with static call information, the other thing we can do is say, we saw this abstract noun as part of the input to this call site. So how do we try? Well, we're going to have yet another tree-shaped data structure. This one's a little different because the other ones were very straightforwardly nouns. This one is, nouns don't have labels at nodes. They're just natural numbers at the leaves. This one actually needs labels at the nodes. So at the nodes of the tree, we're going to record the call site and where in the input. So when we say access, we're just talking about one of these bit streams that defines a place in the tree. We're going to record where it came from. And we're just going to track this all the way through. We're going to filter this for scope because once we're outside the scope of an analysis, we don't care anymore if it flowed through from somewhere else. We just care about, for our call sites, children of this call site, what do we need from this? And then when we go into a call site, all we have to do is tag it and say, okay, in addition to everything else you know about the provenance, it also comes from this new call site at axis 1, which is to say right at the root of the tree. And if we can do that, then when we get to a call site, we just look at the provenance that came to that call site, the provenance for what we know about what formula we're going to call. We can go back to a table that we're keeping of all of our call sites and just record we needed this part of this one subject, this part of this one subject, this part, just based on what that provenance tree says at the call site that we're evaluating right now. So we're literally updating, if we remember that, that very simple mass data structure that's just a tree with bit leaves, we're updating one of those for each call site that is a parent scope of the call site we're evaluating now. And then when we return something back, back out of the analysis, that's where we filter it for scope. Okay, so that's it. We can figure this out, and we can limit knowing what we need. So now we can actually catch recursive calls. So we're just going to keep a stack of our enclosing call sites. We'll check when we get to a new call site. We'll walk up the stack, and this can actually be optimized. You don't literally have to linearly walk the stack, but you can check each new one for compatibility, which is to say, like, could this new call site, what we know here, be one of these call sites already in the stack, right? Does it have the same information? If it does, then we think it's recursive, but we don't know because we haven't finished analyzing the enclosing call site yet. So when we're all done, and we step outside our loops, this is the only, I've worked very hard to keep fixed points out of this analysis. Turns out to analyze recursion, at some point you need a fixed point. This is the only fixed point. So you're just going, and the only thing you're fixed pointing on is that need data structure, and the termination argument is that saturates very quickly. You can only add needed places in that tree, and so in the worst case, you'll discover you need the whole thing. More likely, it will converge very quickly, or you'll discover it wasn't actually recursive. So if we find out that after all it wasn't recursive, we're just going to turn it back into an indirect call. We're going to say, okay, we're going to not know this call site in the analysis. I have instrumented the code while analyzing the Hoon compiler, Arvo, which is the Urbit operating system. I've yet to see the instrumentation fire for that. So in practice, this isn't a problem. In theory, you need to do this for correctness. All right, so Nock is trees. Our formulas are trees, and it operates on trees. We can allocate SSA variables. We have eval and no calls, which makes life difficult, but we can recover the static call information by tracking what we're assuming about the subject and the provenance. One more nice thing falls out of this, which is that in prior versions of the analysis, before you could minimize the assumptions, there was a question about, okay, what if I initialize it with too much information? Then maybe I will record more assumptions than are strictly necessary for this. And so now I have to think about, at the points where I'm actually initializing the analysis, how do I mask it out? With this, you don't need to do that. We literally just, the analysis starts with, we would like to run this Nock against this subject. So, and because Nock can be recursive, we can guard our analysis by checking a stack. Of course, Rice's theorem means that we can't, this isn't actually the full guard we need. At some point, you just have to have a counter, like how deep you are, and just say, okay, we give up past a certain depth, right? Because you could write arbitrarily perverse non-termination, because it is Turing complete. So this actually works. I wanted to show like booting a full Arvo, but it turns out that the nested loops in the Hoon compiler play heck with how I memoize things right now. And I was working on a solution to that on the plane. It's not done yet. So let's pull, where's my cursor? There's my cursor. All right. Let's pull this over here. So what you're going to see is this boot, this is what we call the baby pill as we're developing this. This is an Arvo-like thing that doesn't have to run the Hoon compiler, right? And the behavior it has is literally just to tell the execution environment to print the word effect whenever it receives an effect, right? So it is a full Arvo-shaped kernel, but it doesn't actually do all of the Arvo things just because of the perversity of the Hoon compiler. But the other thing you're going to see, just because I wanted to prove to you guys that we're analyzing this all the way down to an IR, I've printed out the labels of the instructions. So I'm not printing out all the register information and everything else, but I've just printed out the labels of the instructions in this SSA IR that we're running. And I can also show you the actual IR that we come down to after this. But let's just see this go. Right? Like right away it's there. And every time I press enter to feed it another effect, it runs a bunch more instructions and then prints effect. Right? That's it. So this is a full Nock kernel running this whole analysis. There's no indirect calls in here anywhere. So this is a direct call instruction right here. When it says call, that means we knew what the call target was and we just jumped to it. So I promised to actually show you the IR, so let me. All right, so let's go up here a little bit. So the IR is two kinds of instructions. We have block internal instructions, which can only do data flow or like hint type things, right? So for instance, this is an immediate. This just says put this noun in this register. This is a move, right? Copy this register to this register. This is increment. Cons, take the head of a noun, take the tail of a noun. This is stack trace hinting information. This is lifecycle tracking information. Printf debugging hints. And then just down here, we have instructions that can only go at the end of a basic block because they're control flow instructions. So we have branch on whether this register is a cell or an atom. We have branch on whether the things in these two registers are equal. Branch on just an actual Boolean value. Go to another basic block. I don't know if anyone follows me on Twitter, but I forget his name. The Hunim guy was teasing about SSA fee instruction, being just being come from instructions. And there literally is a come from instruction in this IR for analysis purposes only. It's not in what you execute, but it's there to support optimization passes over the IR. This is an indirect call instruction, right? So this is what we build when we actually couldn't discover the direct call. There's none of those in what I just showed you. This is a non-tail call. This is a tail call, but without knowing the call target. And this is a tail call. And the F suffixed ones are just, actually, we think there's a jet here, right? So we're compiling in, hey, you can jet this at static call sites. And then this is return, this is crash. This is because of the silliness that is the namespace read stuff in not Nock. But that's the IR, right? This is like, this doesn't look exactly like LLVM or something else, but this is very obviously something you could just feed to LLVM or feed to CraneLift or transform into whatever your low-level instruction set is, right? You can very easily imagine just like generating machine code straight out of this. All right, so at this point, that's what I have for you guys, and I'm really happy to take questions. Yes?
I have a related question. So, in Nock, is there a way to ensure that a value is like not observable for optimization purposes? Imagine you have like a big tensor and you want to multiply it by another one. A lot of the performance from that is going to be like actually having the tensor represented in memory as like a number. Is there a way to represent it at data level?
So that's what we're tracking. That's what we're discovering and tracking. You can't, like, you could presumably, if you knew that information as the programmer, feed it to this runtime with a hint. But this is actually what we're tracking with.
So you can't like just like rapid enclosure or something like that.
No. This is kind of the point of not. But like actual non-observability in terms of the result is what we're tracking. When we look at that tree, there was like the split case and the register case, but there's also like a we don't need this case. So this information is discovered and tracked. It very much is exactly that. Yes?
What's the, like, how much work do you have to do computationally at pile time to get to this IR? Presumably, there's not a lot of runtime overhead once you've got this IR.
There's basically no runtime overhead.
But the pile time, like the actual analysis, what order of time is this kind of stuff?
So the only places where it's non-linear is just in that loop fixed point. And that is mostly going like.
It's like
I haven't done the full analysis, but again, you're trying to converge on a tree with bit leaves. It's not going to converge slowly.
Are the trees that are produced by these Nock programs that you're analyzing very deep? Like what control?
The trees that are produced could be arbitrarily deep, but that's not what you're converging on in the fixed point. What you're converging on is the tree of what you need from your input. And those trees are, in practice, very shallow. I have instrumented, like, watched what trees you're getting out of that. Those trees are, in practice, quite shallow. And again,
What depth are we talking?
6 or 7 layers deep at most. It's just like basically what happens is, for things that would be really deep, you wind up needing most of it and discovering that ahead of time. So when you actually get to the fixed point, like the actual, and we are very careful to normalize the tree too. So if you say, I need the left and I need the right, that normalizes to, I need the node very quickly. By the way, if you guys want to jump in where we can discuss this, there's an Urbit group for this, and this QR code will actually, like, from your phone, get you an Urbit planet and drop you straight into my group. Neil.
What is the persistence of the cache call site information? How long does it live?
So the call site information is not cached, it's written into the generated IR. So the actual question is, what's the life cycle of the generated IR? And the answer to that is effectively, you can label indirect call sites in such a way that you can say, okay, I saw a new thing at this indirect call site. So this is effectively what var does, right? But in var, every call site is an indirect call site. So this allows us to do ahead of time analysis the first time we want to run something and cache it. So like you can imagine, like, the entry into Arvo would be one of these. The entry into a vein, which are, so Arvo is a microkernel and the veins are the actual, like, operating system services, would be one of these. Entry into a user space agent would be one of these. Roughly, that's the set of places that you would actually have to track the life cycles.
Will this enable fast boot?
Sorry?
Will this enable fast boot?
No, my wild proposal is what enables fast boot. But this will analyze, so the current jet labeling system is a nightmare, and I have a proposal to fix it. I do analyze the current jet labeling system, which is, like, if you actually go and look at my source code where 90% of the complexity comes. And I have a accepted Urbit improvement proposal to fix that, which Matt Levan, who sadly couldn't make it here, is working on right now. And that will enable fast boot because there won't be extra interpreter state necessary to run them. So we can get rid of all the traps to run the jet hits. Liam.
The new application model does, like, a whole bunch of, like, user-facing metaprogramming. So it's like, the prototyping cell stuff that we
Right.
have is, like, basically
Right.
running. Like, is it, like, is it in general possible to just, like, run stuff with the intention that, like, I probably don't need to optimize this because it's only exist once?
So the answer is that's not built into this right now.
Yeah.
But straightforwardly, this is what the hints are for in Nock. You could just have a hint that says don't, right? And then just run it through a bytecode or tree walking interpreter. That would be perfectly fine. Other questions? Liam has another question.
How much faster is it than, like, the current one we have?
It isn't faster right now for a really dumb reason, which is that the actual interpreter for that IR right now in Rust is literally like doing noun lookups for each label. Like, I've spent all the time on the analysis and haven't compiled it down to a bytecode where you get, like, a pointer graph for your call site labels. That's it. Right? It's not slower than var with that in place. And we're also, like, actually still doing the dumb thing to look up jets, like the jet label's written into the code, and then you still have to go look and see if there's a jet. Again, because at the bytecode layer is where you would compile that into just a pointer to the jet, right? So it isn't slower than var, and there's a bunch of things that will make it a lot faster. Anybody else? All right, thank you so much, guys.